Okay, YouTube, this is my first in a quick series of videos on radical notation and how we can rewrite radical notation into what we call rational exponent notation. And then just how we kind of interpret our results with these things. So let's go ahead and start by kind of looking through my reading points here. It says we can extend the concept of a square root to other types of roots. So for example, we say 2 is a cube root of 8. But because 2 to the third power equals 8 and say 3 is a fourth root of 81 since 3 to the fourth equals 81, the idea here is this. In general, we say for an integer n, and we'll say n is greater than 1, we say if we had some base to the power of this nth power, and it came out to be equal to a, then we say b is the nth root of a. So first of all, let's label this here. I'm going to put this in a different color. We say it's the nth root of a. And the reason why we call this the nth root of a is because when we take b to the nth power, we get this a. What we're going to be doing is necessarily rewriting it in kind of a different way, but we call radical notation. We say an nth root of a, we could also write as this. We could say, well, it's a root of a, so we're going to be using this notation right here, and this is called a radical. Okay, this radical symbol right here. So this is called a radical symbol, and we say an nth root is expressed by putting this n on the outside. Now, we are used to seeing this a lot of the time in math. We say something like this would be a square root in particular, and this is as good a time as any to indicate this right here. If we were to write a square root, technically speaking, and we say put a number out here, we'd be putting a 2 because it is a square root, but in general we put an n out here, so we could say this could be a 3 or a 4 or a 5. But what we're really asking is this: what number could I have taken to the nth power to get this thing on the inside here, get this for an answer here? And we say that the answer would be b. Okay, so in other words, b is the nth root of a because we're asking what could I have taken b to the power of, what could I have taken to the power of n here to get a for an answer, and b would be our solution here. So in general, we could write this with anything on the outside here. So we're going to rewrite this, or actually not rewrite this, but give this a name. This number on the outside, I'm talking about this number right here, this n, okay, that indicates the power that we're discussing here. This is called the index of the radical overall. The stuff on the inside is referred to as the radicand. Okay, we refer to that as the radicand. So, for instance, we could re-express this up here. We say the fourth root of 81. We were, discussing it. We say the fourth root of 81 can be written this way, and we could say, well, what is the fourth root of 81? And we say what we're really asking is what could I take to the fourth power to get 81? So I could, guess 2. 2 to the fourth power is 16, so too small. 3 to the fourth power, well, 3 times 3 is 9, so 3 times 3 times 3 times 3 is 9 times 9 is 81. So we say that this would be a plus or minus 3, but only because when we take plus or minus 3 to the fourth power, would we get 81 for an answer, a positive 81, mind you. Whereas, we say 2 to the third power equals 8, well, then we could say, well, then the cube root of 8 is equal to 2 and only 2. And actually, I want to talk about this because we say 2 to the third power is equal to 8. If you were to try to take negative 2 to the third power, you would not get a positive 8 here. So it's a little bit different when you're talking about even roots as opposed to odd roots. An even root is going to give you plus or minus answers, and an odd root, if you have an odd index, you just get one answer, and we'll talk about this. So one main emphasis of this video was kind of to introduce this idea of radical notation, but talk about how we could express it in what we call rational exponent notation. So what I'm going to do is I'm going to take us through just like a really brief argument here, but we can actually write the nth root of something as a power of a. That is, we could take something that looks like this, the nth root of a, and we can rewrite it as a to the power of something, which is a really desirable thing. The only thing is, what is this power right here? So we want to figure out what this power is. What we're going to do is we're going to pursue the example of a square root. Now, this first argument right here, we say square root of a times the square root of a. Using our properties of radicals, remember the square root of a times the square root of b is equal to the square root of a times b, which means we could multiply this stuff on the inside. And if I'm taking the square root of a times the square root of a, I'm taking the square root of a times a, which is the square root of a squared, which is just a. Okay, so you can see how my first argument here is that the square root of a times itself is equal to a in general. And we say what I'm really interested in doing is rewriting this radical notation as a to the power of something. So you can see that this, in essence, when we write it as an exponent, is our base of the exponent, what was in the radicand. And we see that we could rewrite these radical notation as a to the k. So now we don't know what k is, but I can tell you this: we're taking a to the k times itself, and we say it came out to be a in the end here, a to the first power, mind you. So we say a to the k times a to the k. Knowing what we know about the rules of exponents, we say anything multiplied together having the same bases, we're going to add their exponents. So we get a to the k plus k, which is a to the 2k, and you can see that I've arrived at that here. We say a to the 2k then has to be equal to a to the, and you notice I put in a 1 here. So now this is interesting. We say a to the, say, x equal to a to the y. This is actually called the one. This has nothing to do with functions here. We call this the one-to-one property. And the reason why we call this the one-to-one property is because two things that are, look literally identical except for one thing out of place here, we would say these two things would have to be equal. So we say x equals y. Well, in this case we have 2k and a 1. We say 2k equals 1, and we could solve for k now by dividing both sides by 2. And what we end up finding out is this: k would have to be equal to a half. So what this really means is, going back up here, we say a to the k is what we replaced the square root of a with. What we're saying is the square root of a, which technically, I'm going to write this out here, has a 2 out here. We say could be rewritten as a to the 1/2 power. A to the k, which was equal to a to the 1/2 power. So this is pretty profound that we could write the square root of a as a to the 1/2 power. And what I want everybody to see is, well, I say this up here, we say we could write a, the square root of a as a to the 1/2 power. In a similar way, we could show that the cube root of a is equal to a to the 1/3, and the fourth root of a is a to the 1/4. In general, we have this. Basically, we say the nth root of a can be rewritten as a to the 1/n, and this is actually kind of an important thing to be able to do for, at least right now, rewrite things in rational exponent notation. So that means this: we could say, going back to what we were using before, we say the cube root of 8, which we had written this way, we could rewrite it as 8 to the 1/3 power. And it still asks the same question. We say, well, then this would be what? What could I take to the third power to get 8? We say just 2, positive 2 as a matter of fact. And we say that the fourth root of 81, which we had considered, could be rewritten as 81 is the base to this 1/4 power, 1/4 power. And we still get plus or minus 3 in this case, and still get 2 answers. So what I want to do now is at least comment on this. Why did we get 2 answers when we had an even index, and why did we only get 1 answer when we have an odd index? Okay. So really basic commentary on real nth roots, and let me cross that out. I don't want to cross off this text here, but we say let n be an integer greater than 1, and let a be a real number. You notice that we've been using this a, ever since the beginning here. A is the inside stuff here, and the radicand. We say the radicand is a. And we say n is the root that we're using, the index that we are using here. So we say let n be the root or the index, and it's an integer greater than 1, and let a be some number we're taking the nth root of. Okay. We say if n is odd, so this is kind of like harkens back to this case here. When we have the cube root of 8, what I'm saying here is this: when n is odd, then we say a has one real nth root. The important thing here is that it has one nth root and it's real. Okay, so we'd say the nth root of a equals a to the 1/n, of course, equals some root of this. Okay, but the point here is that you get one real answer. So when you have, let's just write this. We say the nth root of a, and we say odd. In the odd case, okay, in the odd case, we say one real answer. I want to squeeze this in somewhere. That's basically what that's saying. So now what if we have an even case? And we say even in the sense that we're taking the nth root of a and n is even. We say we're going to get 2 answers, 2 nth roots. And I'm going to say they could both be real or both be imaginary or complex, okay? But it says if n is even, but we say the inside of this stuff. So the thing we're taking the root of right here is positive, okay? Then we say n has 2 real nth roots. So we get 2 answers, just like when we took the fourth root of 81. We say 81 in here was positive, so we get plus or minus 3. We get 2 real answers here. But we say we get plus or minus the nth root of a, which is of course plus or minus a to the 1/n. We could rewrite it that way. But we get 2 real answers, okay? So now, here's a kind of an important one. We say if n is even, so we're taking an even root. So this is like the 4th root or the 6th root or the 8th root. We could get 2 real answers, right? But I say if a, the stuff on the inside, is 0, that is, if we're taking the nth root of 0, or 0 to the, this should be 1/n here, not 1/2, but 1/n, then we get 0. So the nth root of 0 is always 0. And then this one here, this basically says for right now, if n is even, that is, if you're taking an even root, and a is less than 0, a is negative, okay? Basically, then you're not going to get any real roots, okay? You get 2 imaginary roots, but that's for a later discussion. We'll just say, look, for right now, you don't get any real roots, okay? So what I want to do is I want to find these indicated roots down here, And start by identifying a few things here. So we say find the indicated real nth root of a. What we're saying here is that this is our root. This is our root. And when we write this in radical notation, we say this is our index, okay? And this is our radicand, okay? When we write it as exponential notation, we say it's also the base. So we say in this first instance, let's go ahead and rewrite this in radical notation. We say negative 125, and we want to take the cube root of this. We're really asking the question, what could I take times itself 3 times to get negative 125? And so first things first, let's do this. I also want to rewrite this in exponential notation, so to the 1/3 here. But I would think that negative 5 to the 3rd power equals this. So we'd say that this is our root right here, but we say negative 5. Negative 5 is our root, and we got one real answer. So one real root. And that root was negative 5 because when we take negative 5 to the 3rd power, we get negative 125. So let's try this one here. I notice that I have an even index this time. And my base in here, when we rewrite this, I say base because we could say this is 16 to the 1/4. Same thing. We're asking what could I take times itself 4 times to get 16. And the interesting thing here is you could put a plus or minus 2 to the 4th power and still get a positive 16 for an answer. So this is our root this time, but I'm going to say it's plus or minus 2. And we got two real roots in this instance. Okay. And last but not least, we say, how about the 5th root of negative 32? So then, if I want to write this in exponential notation, notice that I have to put the negative on the inside here of the parentheses because it was included in our radicand. And we say this is the 1/5 power. We say, what could I take times itself 5 times to get a negative 32? Well, it'd have to be one answer. It'd have to be negative, and I'm thinking it's got to be a small number because, taking it to the 5th, it didn't get very large. So we say negative 2 is our root here. So negative 2 and just negative 2. But that is how we express radical notation, rewrite it in exponential notation, what kind of answers we get, and how we kind of evaluate these. Cheers.